Hello, how's it going? In the last video, we were setting up the swap chain and we got that going. Now the swap chain is the procedure for showing images on the screen, but of course we didn't see anything on the screen. So the next step is to set up the graphics pipeline. That is basically when Vulkan gets data describing how to take the data and draw it on the screen. There are a bunch of stages in the pipeline. Some of those are fixed. We do not have much control over them, although we will have to set some parameters. And some of them are programmable. We'll be looking at the programmable stages in today's video, specifically shaders, pretty much. So the big difference between Vulkan and OpenGL is, although they both pretty much use the same shading language, they interpret it differently. So with OpenGL, you can just type your shader in a text file, pretty much, or a string if you want, and just load it in, and it works straight away. In Vulkan, in order to standardize the systems, you can type it up in, GLSL, and then compile it into an intermediate bytecode called SpearV. SpearV, I don't know, SPV. And what that does is it eliminates, well, first of all, the compilers from SpearV to machine native code are more efficient, and secondly, it eliminates some of the issues with running the same program on different systems, and it's sometimes working and it's sometimes not working because graphics card vendors sometimes implement their compilers in slightly different ways. Anyway, I've talked enough. Let's have a look at it. So to start with, we'll have a look at these shaders that I wrote up, and we'll look at how to compile them. We'll look at how to get them into the program. So what I'm doing is, in this case, we're going to draw a triangle, and just to test that the thing works, we are not going to take any vertex input. We are going to hard code it into our shader. The reason for that is, I forgot. Let me just, make this a little more readable. Okay. The reason for this is that the task of getting information from the computer, from the CPU, into the graphics card is, it's not too bad, but it's non-trivial. So we're going to leave that for now. Just get something on the screen first. I'll just note that Vulkan uses a different coordinate system to OpenGL. Typically in OpenGL, for Y, 1 is the top of the screen, -1 is the bottom. That's actually reversed in Vulkan. Otherwise, it's pretty much as you would expect. So we've got a bunch of positions. So for example, this is centered a little bit above center. To the left, a little bit below center. To the right, a little bit below center. So it's a triangle. And we also might want to define a color for each of the corners of the triangle. Okay, fair enough. So this should be familiar if you've done any OpenGL stuff. We're using 4-dimensional coordinates. Z is set to 0. Z of 0 is at the level of the screen. A Z value of 1 is behind the screen, so further away from the screen. And a Z value of negative is closer towards the viewer. However, in Vulkan normalized coordinates, it just goes from 0 to 1 for Z. And a depth coordinate of 1, that's just standard for a 4-dimensional system. So this GL position is a global variable. We're setting that, so we're setting the position that we're passing on to the, the rasterizer to make the shape. And this GL vertex index is a global variable as well. So every time the every time the vertex code, or the vertex shader is invoked, it's saying, hey, let's draw a point, and by the way, we're drawing point number 0, we're drawing point number 1, and so on. So that happens automatically behind the scenes, and that is what we can use to vary the positions and colors for this example. Great, we pass it on to fragment color, which is an output variable. And then when we go to the fragment shader, that takes it in as an input variable, stick on an alpha of 1, and pass that out as the color to display on the screen. Awesome. So the next question is, how do we take this and put it into SpearV? So there's a bunch of ways we can do it, but basically we call this, we execute our compiler. So this is glslc, GL shader language compiler.exe. The input file is the name of our file, and this, if you've done C compiling, GCC or something, this is a common flag for declaring an output file. Will be called, in this case, vertex.spv. So we can run this, and it works just fine. For instance, let's grab this up. This is my thing. What do we do? Just whatever one we want to use. I will use git bash. We'll say in our current folder, run compile.bat, and it tells us which commands were executed, and there's no error codes, so that works. Something to bear in mind is that we need to, so what's this one? Shader.vert. So these need to be in the .vert and the .frag formats. For example, if I write vertex.text, which is a common way to handle this in OpenGL. In OpenGL, this would be perfectly fine. We just say, okay, we're taking as our input vertex.text. Now, if we try this, we'll say file is not recognized, file format not recognized. So it needs to be a .vert or a .frag, respectively. And I think the reason for that is it does a little bit of work behind the scenes, adding extra like metadata and stuff. And then we'll just fix this up. Yeah, but that's fine. We've got that already compiled. So that's cool. Now what we need to do is we need to be able to read that data, because we have this .spv thing. We need to get that into C++ and read it, basically. So that will be this function here, ReadFile. I'll have a look at that in a second. But first of all, let's have a look at how it's used. So we're going to go to this create graphics pipeline function, which I've written. Okay, first step is we need to read the files. We call that in with this vertex.spv, okay, and then we'll do a bit more work with that. So we take that, that's basically the raw binary data of the file is stored in these variables here. We pass that into this create shader module program, and what that does is it passes, or does it pass or compile? I don't know. I'm pretty sure it compiles. It compiles it into the native code and returns basically like a shell, like a wrapper around that shader module, which is then used in creating a shader stage. Okay, so I mean, you can grab the code, you can have a read through it. I could talk through it, but then this would be a long video, needlessly long. So we grab those shader stage infos and we stick them into an array, because those will be used later on when the graphics pipeline is fully completed. This is just the programmable stages. In the next video, we'll do the fixed stages, and then we'll be using this info in our fixed stage, and then that'll be it. Okay, yeah, and then as it says here, we can destroy those shader modules after they've been read, after they've been used, because they're not the shader modules themselves, they're like a wrapper around the code. Cool, so now let's have a look at the reading. Okay, so we take in a file name, we want to output a vector of characters. So we have this input file stream, and in order to use that, we need to include this file stream header, but that's fine. Okay, so we open this up and we have a bunch of flags we set. We want to start reading at the end because we need to get the file size in bytes in order to reserve enough space on our vector, and also to know how many bytes to read from the file. And we specify that we're not reading text data, we are reading raw binary data. Cool, okay, so we use this tellg function to get the position of the read head of the file. That tells us basically how many bytes are in the file because we started reading at the end, and then we reserve that space in our return vector, rewind to the start, and then just read everything. So this is a pointer to the beginning. This is a pointer to the beginning of the variable where we're going to start writing the data in that we read. And this is the number of bytes we want to read. Awesome. So that's set up. Cool. So the last bit is down here, this create shader module. So we take in a vector of all the raw binary data and we use that. Okay, so as you can see here, we're creating a shader module. We pass in the size of that. And then the only thing here is, because this is expecting the data to be 32-bit unsigned integers, but it's characters actually is what we're passing in, we need to do a reinterpret cast. Of course, a character basically is an unsigned 32-bit integer, but we need to make sure that it's being interpreted that way. And remember, of course, calling .data returns a pointer to the start of the variable, which is what P code expects. The difference here, okay, the difference with one type of pointer compared to another type of pointer is, for instance, let's say that we had a pointer to a 64-bit integer. 64-bit, yeah. So the difference is you'd read that, you'd be able to access that, and when you dereference that pointer, it would grab from the beginning the first 8 bytes of data. And then when you increment that pointer, it would look at the memory location 8 bytes along in memory, compared to if you did that as a, I don't know, a 1-byte pointer, like a short or something, then it would, a really short, then it would read 8 bytes of data when you dereference the pointer, and then when you increment to the next pointer, it would look, sorry, not 8 bytes, 1 byte, 8 bits. When you increment the pointer, it would look at the memory location 1 byte, on in memory. I mean, that's it. Alrighty, so what are we doing? Yep, so we create a shader module, call the create shader module function, return that. And that is what we are using up above. We just call that function to grab the shader modules. Okay, so that's it. That is the programmable pipeline stages done. In the next video, we'll be looking at the fixed pipeline stages, and we'll be getting there. After we've got the fixed pipeline done, we will then need to look at setting up draw commands, because nothing's straightforward, but with being explicit, we do get a lot of power. Anyway, that'll be it for now. Have fun. Bye.